remember the law of kinetic energy in classical mechanics. You know, the work equals the change in kinetic energy. Let's see if there's something similar in relativity. In the last YouTube short, I showed the general force formula given by this. And here I want to say that m here is the relativistic mass in order to avoid all those gamma factors that we normally see in the literature. Anyway, it's a simple formula expressed like this. So let's look at the definition of work. It's the integral force dot dr, and dr can be changed with the velocity dt, and then we can multiply velocity into this general formula. So you will get v squared and a dot v. This is what you see here, v squared and v dot a. And also the t is still there. Okay, and then we break out m v dot a, and you get those two terms here, which can be simplified into this. And in general, v dot a can be simplified by this simple formula here, the speed times the v dt. All right, so then we can simplify the integral to this. And the primitive function of this integrand is simply mc squared. And the limits here is dv now. You know, dv dt dt, that's dv. So the limits are from v1 speed, v1 to v2. And you put it in here. And still realizing that m is relativistic mass, so it's including a term like this. And here's the rest mass, m naught. And then you get this. And the difference is here, m2c squared minus m1c squared. And the difference here is really the difference in kinetic energy, T2 minus T1. You know that kinetic energy is defined really like this, mc squared minus the rest mass energy. But in a difference, this constant will just disappear. So in fact, this is exactly right what I'm saying here. And here as a bonus, let's Taylor expand this relativistic mass, you get this, and then you can see that the relativity kinetic energy actually boils down to our standard 1/2 mv squared.